The human ribcage operates under intense biomechanical demands. It is a highly dynamic structure that must maintain structural integrity while under the constant respiratory load of cyclic expansion and contraction. When blunt force trauma or tumor growth damages this framework, repairing it requires a highly precise reconstruction. But navigating the immense interpatient anatomical variability and the complex 3D curvatures of individual ribs makes this incredibly difficult. A custom thoracic implant has to precisely match the missing bone morphology of the patient. It must integrate seamlessly into the native skeletal framework and align perfectly at the costovertebral and costosternal junctions. Right now, designing these specific implants is a manual, labor-intensive process. Surgeons rely on clinical engineers working within computer-aided design, or CAD, software to custom build every piece. The engineers interpret raw CT scans, manually delineate the exact defect boundaries across dozens of cross-sectional slices, and painstakingly model the replacement geometry by hand. This expert-driven dependency takes time. In emergency trauma situations or urgent oncologic resections, patients cannot wait days for a custom CAD model. This workflow creates a strict bottleneck preventing rapid intervention. Researchers have developed RibCageImp to solve this scaling problem. It is the first fully automated, data-driven deep learning framework engineered to generate 3D ribcage implants directly from patient CT volumes. Previous computational solutions relied on statistical shape models and template-based deformations. By taking an automated volumetric approach instead, the system adapts to unseen anatomical variations, offering consistent, scalable implant generation. The core of the framework is built on a 3D unit. This is a convolutional neural network architecture, specifically tailored for high-resolution volumetric medical image analysis. The 3D unit uses a symmetric encoder-decoder design. It captures multi-scale spatial features from the scans and uses skip connections to fuse them, allowing the network to parse both local rib morphology and global chest wall structure at the same time. To increase representational power, the model integrates a pre-trained EfficientNet B0 encoder. EfficientNet utilizes compound scaling and depthwise separable convolutions, extracting structural features efficiently from complex medical images without requiring massive computational overhead. Mapping a defective ribcage volume directly to a predicted implant volume eliminates the need for manual boundary tracing. It allows for end-to-end learning tailored exactly to each specific patient's missing anatomy. Training this network requires extensive volumetric data. The researchers utilized the RibFrac dataset, which provides high-resolution thoracic CT scans with explicitly annotated bone structures. The algorithm first applies value-based thresholding and morphological operations to the raw scans. This strips away noise and soft tissue, isolating clean, contiguous bony segments. To teach the model how to fix a broken ribcage, the researchers had to synthesize thousands of defects. They programmatically carve out 3D patches from the healthy bone segments to simulate the effects of high-impact trauma or surgical removal. This creates exact input-output pairs for the network. The residual, damaged bone, acts as the input condition, and the synthetically carved-out piece serves as the perfect target the model must learn to predict. In this data pipeline, a zero-mask MD embedded into the bone volume SG extracts the defective ribcage RD. In parallel, mask MI isolates the ground truth implant IG. These paired volumes are then resized into standardized grids of 256 by 256 by 128 for consistent network training batches. Automating the creation of synthetic defects supplies the deep learning framework with the sheer volume of data necessary to learn structural reconstruction across a massive variety of rib geometries. During training, the accuracy of the model's output is governed by a loss function, a mathematical objective that scores structural similarity and penalizes errors. The standard metric for medical segmentation is the Dice similarity coefficient. It measures the global spatial overlap between the model's predicted implant volume and the exact ground truth. This 3D visualization demonstrates why Dice loss alone is insufficient. A high volumetric overlap score confirms the general bulk is correct, but it ignores the fine-edged boundary misalignments that are common in the sparse, highly curved geometry of individual ribs. To tighten structural accuracy, the framework incorporates a second metric, voxel-wise mean-squared error, or MSE. Here, the grid maps intensity differences. MSE penalizes spatial deviations voxel by voxel. This forces the network to produce finer details and smooth, continuous reconstruction surfaces. These standard vision metrics completely lack the anatomical constraints required for surgical safety. The first major surgical risk is anatomical overreach. If the network predicts extraneous bone structures, the generated implant will protrude beyond the intended boundary of the native ribcage. An implant that protrudes inward creates hazardous overlaps with critical soft tissues and vital organs like the heart and lungs, making it entirely unusable. To prevent this, the researchers designed an anatomical boundary loss, or ABL. This custom constraint explicitly suppresses false positives by heavily penalizing any predicted voxel that falls outside the true anatomical boundary. The inverse risk is underprediction. If the model fails to fill the entire defect, it leaves structural discontinuities and gaps that compromise the biomechanical stability of the reconstructed chest wall. The solution is the defect completion loss, or DCL. This term penalizes underpredicted voxels, forcing the model to generate an implant that is completely contiguous with the surrounding bone. ABL and DCL are integrated directly with DICE and MSE to form a single 4-term composite loss function. These novel constraints force the network to respect the physical limits of the human body. The process shifts from generic voxel regression into anatomically informed structural engineering. The framework was evaluated under 2 distinct clinical scenarios: isolated single bone defects and severe multi-bone trauma, where several adjacent ribs are destroyed. To evaluate performance, the researchers utilized the Hausdorff distance. This geometric criterion measures the maximum surface deviation in millimeters between the prediction and the ground truth, making it a strict test for boundary alignment. This chart displays baseline performance for multi-bone defects. Standard training yields severe surface deviations, a Hausdorff distance over 200 millimeters. As anatomical boundary and defect completion losses are introduced, performance sharply improves. Boundary errors drop significantly, pulling the Hausdorff distance down rapidly. Under the full composite loss, the model hits its highest accuracy. For single bone defects, it achieves a DICE score of 0.3521 and drops the Hausdorff distance down to 110.9 millimeters. This confirms that it takes multiple, highly specific loss terms working simultaneously to accurately map the complex topology of the thoracic cavity. To understand what these numbers actually yield, we must examine the qualitative visual outputs to judge the anatomical plausibility of the predictions. In this technical comparison for multiple rib defects, look at the bottom row. Guided by the full composite loss, the predicted implant, IP, accurately conforms to the expected curvature and blends directly into the defective cage, RD. The single bone reconstructions here display excellent spatial coherence. In the final row, the geometry of the predicted implant closely matches the curvature, thickness, and volume of the actual ground truth. Still, the human ribcage is highly non-uniform, and certain complex geometries continue to expose limitations in the network's current design. Case A outlines a clear over-prediction failure mode, generating extraneous voxels visible as extra floating geometry. Case B highlights the inverse failure. The network underpredicts the necessary volume, leaving clear structural gaps that fail to bridge the defect. Correcting these errors will require larger training datasets and the integration of explicit geometric priors that can enforce exact local curvature across tight intermittent spacing. However, RibCageImp successfully establishes the first fully automated baseline for data-driven thoracic reconstruction. It proves that deep learning can bypass hours of manual CAD labor to generate functional, patient-specific chest implants directly from medical imaging.